Hello and welcome. My name is Margarida and I'm presenting Forest, an interactive synthesizer of regular expressions for form validations. Forest is the result of joint work with Miguel Neves, Miguel Ventura, Inês Lynce and Ruben Martins. Consider a digital form where one of the fields asks the user to input a date, which must be in the commonly used format in Europe, the digits for the day, 2 digits for the month, and 4 digits for the year with slashes as separators. A regular expression can be used to enforce this format. However, writing a regular expression can be challenging for beginners. And even for experienced users, writing several of these validators becomes monotonous and error-prone. So we introduce Forest, a regular expression synthesizer for digital form validations. Forest allows the user to obtain a regex validator based on a set of valid and a set of invalid examples. Forest takes as input the set of examples and returns a regular expression that accepts all the valid examples and none of the invalid. To synthesize regular expressions, Forest employs a commonly used synthesis technique, enumerative search. The enumerator successively enumerates candidate programs from our domain-specific language. Each candidate program is then analyzed by the verifier, who checks if it is compatible with the user-provided examples. When the verifier finds a program that satisfies all user-provided examples, then we can return it to the user. We will start by looking into how Forest enumerates programs within the DSL. The enumerator needs a data structure capable of representing all feasible programs. One such structure used by previous synthesizers is the K-tree. That is a tree in which every internal node has exactly K children and every leaf node is at the same depth. This is an example of a K-tree with K equal 2 and depth 5. The program corresponds to an assignment of a DSL construct to each tree node. The node's descendants are then the construct's arguments. Since the arity of constructs in Forest's regex DSL is at most 2, all regex in the search space can be represented using K-trees with K equal to 2. The enumerator encodes the K-tree as an SMT formula that ensures the program is well typed. Then, we feed the formula to an SMT solver and a model that satisfies that formula represents a valid regex in our DSL. This assignment represents the date validation regex I showed you before. We can see that this is not a very efficient representation for this regular expression. More than half the nodes remain empty. These empty nodes are not being used to represent our regular expression, but they are adding complexity to our enumeration process. We considered several validators for digital forms, and we observed that many regexes in this domain, like this one, result from the concatenation of simpler regexes. Thus, we wanted a structure that allows the number of concatenated subexpressions to grow without it reflecting exponentially on the encoding. And we came up with multi-tree. To build a multi-tree, we need to identify common patterns in the valid examples. To do so, we start by finding dividing substrings. A substring is a dividing substring if it occurs exactly the same number of times and in the same order in all examples. In this case, a slash is a dividing substring because it occurs exactly twice in each example. Then we split each example before and after the dividing substrings, and each split gets its own K-tree to represent the corresponding subregex. In the end, the complete regular expression can be built by concatenating all the subexpressions. Comparing the classic K-trees with our multi-trees, we can see that in the dates example, the multi-tree representation requires only about half the nodes, only 4 of which remain empty. So, we enumerate regexes represented as multi-trees until we find one that satisfies the user-provided example. However, there can be more than one regex that satisfies all the user-provided examples. Coming back to our dates example, both these regular expressions satisfy all examples, and Forest needs a way to ascertain which of them will better suit the user's needs. So, to disambiguate the initially provided examples, Forest employs a method based on distinguishing inputs. In this case, Forest uses Z-tree's regular expression SMT theory to produce a new string, which is accepted by the bottom regex, but not by the top one. This new string is then shown to the user, who is responsible for deciding whether or not it's a valid value for the input field. The user would say in this case that this is not a valid value for the input field, so Forest would eliminate the bottom regex from the search and return the top expression to the user. So we extend our enumerative search Forest by adding a new component, the distinguisher, who, given two correct programs, produces a distinguishing input. This input is then shown to the user, who classifies it as valid or invalid. The input is added to the set of examples, making one of the two initially correct programs now incorrect. This interactive cycle continues until there is only one program left, which is returned to the user. So we have a regular expression that validates the date input field according to our examples. But is that enough? It is not. This regex by itself accepts dates such as the 33rd of August or the 26th of month 0, which are not valid dates in our calendar. We are validating the format of the input strings, but not their values. Then we want to ensure that our dates can only have days between 1 and 31 and months between 1 and 12. We ask the user to provide one additional set of examples, conditional invalid, which are wrong due not to their format, but to their values. Then, we add to our validation a new component, the capture conditions. Our previously synthesized regex invalidates the set of invalid examples, whereas the capture conditions invalidate the set of conditional invalid examples. In the end, their conjunction allows only the valid examples, as was our goal. To validate the values in our string, we need a way to identify in our regex which part corresponds to the day, the month, and the year. To that end, we can extend our regex with capturing groups. A capturing group is a sub-regex within a regex that is indicated with parentheses and captures the text matched by the sub-regex inside them. In these examples, we can see the capturing groups that capture the parts corresponding to the day and the month. We can also have several capturing groups in the same regex, which we can reference using their indices. To synthesize capturing groups, we use the previously described interactive enumerative search. So Forest first synthesizes the regex that is the base for the capturing groups, and afterwards it synthesizes a set of conditions over the resulting captures. To enumerate capturing groups over a regex, we consider parts of the regex which correspond to numbers, and test the different combinations of capturing groups over them. For each set of captures, we use an SMT solver to try to find a set of conditions that are satisfied by the valid examples, but not by the conditional invalid. Once we find these conditions, the enumeration process ceases. After this, we must once again address the ambiguity of examples as a specification. Forest may find more than one set of conditions that are satisfied by the user-provided examples. As before, Forest uses an SMT solver to build a distinguishing input, shows it to the user, and based on the user's classification of this new example, removes from the search space one of the sets of capture conditions. And that's it, that's Forest's synthesis process. To recap, Forest takes as input a description of the desired validation expressed as a set of examples and returns a regex validation that exhibits the described behavior. The user may provide Forest three types of example: invalid, valid, and conditional invalid. First, Forest will use the valid and invalid examples to synthesize a regular expression that validates the format of input strings. Next, using the conditional invalid examples, this regular expression is complemented with a set of conditions over capturing groups which validate the values of input strings. Now let's take a look into our paper's experimental results. To evaluate Forest, we used 64 benchmarks based on real-world form validation regular expressions. These were collected from regular expression validators in validation frameworks and from RegexLib, a website where users can upload their own regexes. Among these benchmarks, there are several different formats, such as national IDs, identifiers of products, date and time formats, vehicle registration numbers, among others. We start by analyzing the performance gain that results from using multi-tree representation instead of k-trees in the enumeration process. We ran Forest with two different versions of the regex enumerator, one using k-trees, another using multi-trees. The table on the left shows the number of instances that can be solved by each method in under 10 seconds, 1 minute, and 1 hour. The cactus plot on the right shows the synthesis time on the y-axis plotted against the number of benchmarks solved by each variation of forest on the x-axis. In this type of plot, the methods that correspond to lines more to the right of the plot are able to solve more benchmarks in less time. K3 can only synthesize 15, which is about 23% of our benchmarks in less than 1 hour. Furthermore, K3 can only synthesize very simple regexes. The synthesized regexes use at most 10 nodes of the K3 representation. Using the multi-tree representation, Forest is able to solve 47 instances, which is about 73%. And in just 10 seconds, it can already synthesize 48% of our instances. Besides speeding up the synthesis process, multi-tree allows us to synthesize more complex regexes. We can synthesize expressions with up to 24 used nodes in a multi-tree representation. Next, we assess the impact that the interaction model based on distinguishing input has in our synthesis process. We run a version of Forest that returns the first validation that satisfies the examples it can find, instead of interacting with the user to disambiguate the examples. As expected, without interaction, the synthesis procedure becomes significantly faster. The number of instances solved in under 10 seconds increases from 31 to 40. However, this comes at a cost. Of the 47 instances that Forest solved in under 1 hour, 45 were correct, meaning that they were the actual regex that corresponds to the user's desired intent. In contrast, without interaction, only 31 of the solved instances were correct. Finally, we compared Forest with the state-of-the-art regex synthesizer Regel. We observed that Regel and Forest can solve the same number of instances in 1 hour, that is 47, but since Regel does not implement an interaction model, it returns the correct regex in only 31 instances. So in terms of synthesis time, Regel is similar to Forest, but Forest solutions are more often correct. I will now show how anyone can try out Forest. Forest is open source and may be found at its GitHub repository. In there, you may also find a link to a Google Colab demo, which allows you to try out Forest in any browser without any installation required. The first 2 cells will download the repository's code and import and define some functions required to show you the synthesis process. Down here, we find our initial dates validation example, including the valid and invalid examples I showed you. Using the synthesize function, we can see Forest in action. It synthesizes 2 candidate expressions and produces a distinguishing input which we, the user, will classify as invalid. In the end, Forest returns the desired regular expression. Further down, we can see the synthesis of capture conditions. We use the same valid and invalid examples, and we add the set of conditional invalid examples. Forest will require 1 additional interaction with the user to disambiguate the examples. In the end, it returns the same regex, along with 2 capturing groups for the day and the month, and conditions that specify that the day must be between 1 and 31 and the month between 1 and 12. Finally, you can edit the last 2 cells to run Forest with your own examples. To summarize our contributions, we propose the multi-tree SMT representation for regexes, which leverages the common structure shared between the valid examples. We described an interaction model using distinguishing inputs to disambiguate the initial specification, thus increasing the user's confidence in the synthesized solution. We propose a new method to synthesize capturing groups for a given regular expression and integer conditions over the resulting captures, which allow us to further constrain the input field validations. Finally, we presented and evaluated Forest, a publicly available tool that implements all the aforementioned techniques. Thank you for watching my presentation. I will now answer any questions you may have.